Hello everybody, today we're going to be looking at a relatively simple trick when it comes to solving integrals, but one I think will be quite useful. In fact, this is one of those things you pick up. I was learning about the Feynman method, differentiating under the integral, and this came up in one of the integrals, so it's fairly useful. So this looks a bit hideous right now, but I will go ahead and explain it, and hopefully after that it shouldn't seem too bad. Alright, so basically what we're doing here is we're going to take, this is to simplify some trigonometric integrals, alright? So it's basically taking the substitution t is equal to tan of x by 2. Now the reason that this is useful is because say we have sine of x, alright? So we know that sine of x is equal to 2 sine x by 2 times cos of x by 2. That's because we have this trigonometric identity, sine of 2x is equal to 2 sine x cos x. And similarly, we know that cos of x is equal to cos square x by 2 minus sine square x by 2. And we know this because of similar reason, cos 2x is equal to cos square x minus sine square x. So using this, we can simplify these integrals. We can start by writing sine of x as what we're going to do now is 2 sine x by 2 times cos x by 2. So this whole thing is just sine x, well, the whole thing. And in the denominator, we're just going to write 1. So sine square x by 2 plus cos square x by 2, which is of course 1. Now, if we divide this whole expression by cos square x, then what we get is 2 sine x by 2 times cos x by 2 over cos square x. And this cancels out with this. And over here we get sine square x by 2 over cos square x by 2. I'm just going to do this mentally because it's easier. Tan square x by 2, and then cos square x by 2 by cos square x by 2 is of course, that is x by 2, is of course 1. So we get 2, and then this becomes 2 tan x by 2 over tan square x by 2 plus 1. So we get, with our original substitution, t is equal to tan of x by 2. We get 2t over t square plus 1. And similarly for cosine, we do something kind of similar. We take cos x as, in the numerator we'll write this form of cos x. So we get cos square x by 2 minus sine square x by 2. Sorry for the handwriting. And in the denominator we get sine square x by 2 plus cos square x by 2. So we're going to divide by cos square x by 2 again. So in the numerator we get, the first term is going to be 1 minus tan square x by 2. And in the denominator we get tan square x by 2 plus 1, which you'll notice is the same as this because the denominator is the same, of course. And this will give us 1 minus t square over 1 plus t square. Now, the final thing that we have to do is, of course, when we want to find when we want to substitute this in our integral, we'll need to find dx in terms of dt. So let's go ahead and do that. We'll take t is equal to, I'll do that in white, t is equal to tan of x by 2. So we know that dt by dx is equal to sec square x by 2 over 2, which gives us dx is equal to 2 dt over sec square x by 2. Now we also know that sec square of x is equal to 1 plus tan square x, so we can write that as 2 dt over 1 plus t square is equal to dx. And so that's how we get this formula. I mean, this is a condensed way of writing it, but basically what we're getting is, and I'll summarize this here, we get sine x is equal to 2t by 1 plus t square. We get cos x, I'll do that in a different line, we get cos x is equal to 1 minus t square over 1 plus t square, and we get dx is equal to 2 dt by 1 plus t square. Now you can use these substitutions individually, you can use them together. What I'm going to do now is I'm going to show you an example of the derivative of, the integral of, I'll do this in yellow, the integral of cosec of x dx using this method. So we can write cosec as, of course, 1 over sine of x dx. Now we know that we can substitute sine of x as this, so we can take this as 1 plus t square by 2t, and we have to substitute this for dx, so we take 2 dt over 1 plus t square, and that's our integral. So what we can do now is we can take we let these cancel out, and we get 2 by 2t dt, which is just, of course, ln of mod t plus c.